Fly me to the moon, let me play among the stars.
Welcome to Science on the Side with your host, Liam Hickey. Tonight we're going to be talking about nuclear energy. We're going to be going in depth on the technology, the future use, the benefits, the risks, and the availability of this resource. We're going to be going really in depth with all of these topics. But to kick us off, we're going to have McKinley Adams, our correspondent, give us some information on the historical context for the past 80 years of this energy. McKinley, go ahead and start it off.
Thanks, Liam. Uranium was first discovered in 1789 by a German chemist. His name? Martin Klaproth. Hey, Martin. Uranium is the basis of most nuclear operations. I say most because plutonium plays a role, but just not as major. Atomic change and nuclear fission was developed from 1895 to 1945, although much of it was developed in the last 6 years due to World War II, and that development was more focused on the atomic bomb than nuclear energy itself. War is fascinating. It has a way of speeding up inventions and inventing things. Think about it. We wouldn't have half the technology we have today if not for World War I and World War II. Anyways, the first reactor used to produce energy started in December of 1951 in Idaho. After this, the growth grew a lot, exponentially, through the roof. Well, we can't break through the roof. By 1989, 109 nuclear reactors were generating about 19% of the nation's electricity, becoming the second largest power source in the U.S. Back to you, Ian.
Thank you, McKinley. So next we're going to talk about the fun stuff, how everything works. So we'll start off nuclear fission. Nuclear fission is the splitting of atomic molecules to produce a chain reaction, which in turn produces heat energy. So a nuclear reactor, it just harnesses and produces that energy. So we're just going to walk through like how that works inside a model. Right, boom, right there. Okay. So we're just gonna walk through it. Is that fine? So right there in the orange and yellow, those are the fuel elements, which consist of fuel rods with pellets, uranium pellets inside acting against the fuel. And there's many rods within the fuel elements. Next, you have the primary circuit, which is the water that runs from the control rods in that steel pressure vessel to the steam generator and back around in a clockwise direction. That is all radioactive water because of the fuel element, the uranium, cause it to be heated to extreme temperatures, but it doesn't turn into steam. The reason is because of the pressurizer. This is called a pressurized water reactor. It's the main one that they use, which is why I'm going through it, and the pressurizer prevents it from turning into steam. But it does keep it very, very hot, so it runs through that primary circuit until it gets to the steam generator. The steam generator has these U-rods. The U-rods are warmed by the radioactive water, and then the water in the secondary circuit up there above the steam generator, that water is heated and turned into the steam because it's not radioactive. Got it? So that steam is then gone through to turbines, a high pressure and a low pressure turbine. These turbines are spun by the steam. The turbines spin another rod. Apparently there's a lot of rods in a nuclear reactor. The rod spins, which is connected to a electrical generator. Now it's making sense. The rod is mechanical energy. It turns in the generator to electrical energy, which is AC current or alternating current. The remaining steam is then transferred back into liquid, into water, and funneled back into the steam generator, as you can see. What's not shown by the graph is a tertiary circuit, a third circuit. That is typically when you think of a model of an atomic reactor, a nuclear reactor, where it's got like the big building that looks like this. You know what I'm talking about? Flat top, but it's open, so it's got like stuff coming out. That's the coolant system. It's just a little pathway that runs from that big guy and back, connecting to the secondary circuit. Allowing refilling of water. It's the reason that a lot of nuclear plants and things are next to rivers and streams. It's to refill it. Now I'm just going to talk about the other kinds of generators, not generators, power plants. This one, as I said, is a pressurized water It's a pressurized water reactor. And then the other one, the secondary design that's used, is the boiling water reactor. This one's not quite as popular. What they have in common is that both types produce steam. Just the boiling water one produces steam in the primary circuit, as opposed to this one, which produces it in the secondary circuit. They both also use water as both a coolant and a moderator. Now, a moderator is what's used to slow down neutrons in nuclear fission to allow for more chain reactions and for more fission to occur. It's an efficiency thing. So now moving on to another aspect. This technology's been around for about 70 years. I mean, McKinley went over all the historical stuff to it, but it's been around for 70 years or so, and as it's gone on, it's been through generational phases of its life. For example, the first generation was Generation 1, properly entitled Generation 1, and it was the prototype reactors that were used. And this was about back in the 70s. Okay, so then the next generation, Generation 2, was back in the 80s. This was the first commercial reactors. Then there was, up until 2010, there was Generation 3, and these were just much of the same, just a bit more advanced in their safety and other precautions. And then from now until 2025, the current generation is Generation 3 Plus. That generation includes evolutionary designs and improved economics and safety for the near-term development. Alright, so then the next term, this is the fun one, is Generation 4, which is the year 2030 and later. Let's talk about the future, which I'll talk about in a little bit. But it's said that this is to be highly economical and with the same goals that all the others have had in their innovation and their process, which would be enhance the safety, minimize the waste, and resistant to proliferation. Cool, so now we're going to talk about the availability of this resource. How easy is it to find? Who uses it? What nations? What organizations? This kind of thing. We're going to go in deep on this. So just to start it off, there are currently 437 operable civil nuclear reactors around the world. And there are another 66 currently under construction. So just the word civil that I used earlier, that means public. So that energy being produced is given to the public as energy sources of energy, as opposed to like being withheld by the government or something. That's what that means. And then there are a series of national and global organizations that regulate this. First of all, the highest tier would be the UN's International Atomic Energy Agency, also known as IAEA. These guys are the top dogs. They make a lot of the laws. The goal of all of these organizations is to keep peace, prevent war, just make everyone have a positive experience from nuclear energy, and that everyone shares in the wealth, everyone shares in the energy, and everyone shares in the technology advancement, which is really, really cool to think about. So the next one that's a little bit less formal and doesn't have the UN's title to it is the World Association of Nuclear Operators, or WANO. These guys, they're big on the non-proliferation thing, which is, as I mentioned earlier, is peace. There's no fighting for nuclear energy. There's no fight for economic. It's peace. That's what it is. Non-proliferation. Next one is the World Nuclear Association. These guys are more based on education, lower tiers than the ones I mentioned previous, but I got a lot of my information from them. They're very, very useful in their data. So next is the fun part. We're going to talk about some different types of ore grades, the quality of the ore. I'm going to throw up a little graph right up here, and that's going to talk about the different. I don't have time to go into that in depth, but as you can see, the best quality ore, if you want the top-notch uranium, go to Canada. It's in Canada. Cool. Next one I want to talk about is that uranium is actually very common. Most people don't know this. People think it's a rare element, but it's surprisingly common. It's approximately as common as tin or zinc, which is crazy. In fact, the world's known uranium resources has increased by at least 1/4 in the last decade due to mineral exploration. Yeah, it can actually be found in rocks, seawater, pretty much anywhere in the earth. And also, I'm going to throw up another graph here about the quantity of uranium that you can be found, like in different geological locations or in different nations. Don't have time to go in depth on this as well either, but as you can see, if you want a lot of ore, you go to Australia. So now that we talked about that, we're going to talk about some of the risks and some of the benefits of this technology. And our correspondent you saw earlier, McKinley, is going to do that for us. McKinley, go ahead and take it away.
All right, Liam. Here are some benefits of nuclear energy. It reduces harmful emissions. For example, nuclear energy produces more than 70% of the nation's carbon-free electricity. And the total U.S. nuclear production amounts to more than 800 billion kilowatt hours, as the third largest energy source in the United States behind coal and gas. And it puts uranium to good use. I mean, if not, it'd just be radioactive material in a mountain. And it increases human and technological capability and capital. Some other advantages are that nuclear power plants are cheap to operate because they make their own electricity, and they have a very long lifetime. There's little land requirements and small fuel and waste volumes because the fuel is a waste, doesn't produce anything extra. For example, 1 pellet of uranium equals 1.5 tons of coal. That's 5,000 kilowatt hours of energy per pellet. Now here's some risks. First, there's no long-term solution to disposing of nuclear waste because it needs long-term isolation and it is extremely toxic. And like uranium isotopes have half-lives of up to billions of years. Okay, the reactors are expensive and take a very long time to construct. Plus they have the disadvantage of having a long payback period. So basically it takes a long time to repay the construction of said reactor. Another risk is evident by the Chernobyl and 3 Mile Island disasters. For those who don't know, these were 2 nuclear power plant meltdowns. Chernobyl resulted in about 30 deaths, and in the 3 Mile Island incident caused no injuries and no deaths. And finally, there's a concern on everybody's mind of nuclear weapons. I'm just going to tell you this, they can't be easily made into nuclear weapons, and they don't really have anything to do with nuclear energy. Back to you, Liam.
Thank you, McKinley. So next we're going to talk about a debatable topic, the last topic we're going to talk about tonight, and that is future use of this energy. So the way I like to look at this is, do not drive into the future by looking in the rearview mirror. And that's just saying, don't look to the past to make what will come in the future. So don't worry about innovation when you can do invention. Talking about that here in a second. So no projections. I'm going to throw some data here about the future projections for this technology. But I don't want to talk about the data so much because, they don't go past the year 2030. That's because there's no way of knowing anything past that. I mean, even up to 2030, there's not much you can know for sure. These are all theoretical. So personally, I'm supposed to get personal here. I think despite this technology's good track record in safety and its incredible clean energy generation, for the future, nuclear energy is just too slow, and it's inefficient in its production, and it is financially a nightmare, as McKinley was mentioning earlier. For those reasons, I think that it will not suffice the needs of the clean energy in the future. I mean, not the grand plans. In the near future, I have a feeling it would do fantastically, even for the next potential 15 years. But past that, when we want to do incredible things like not just powering homes, which is what it's doing, but power the homes of the entire planet, or anything that requires anything but a minimal creation time, nuclear energy, it won't be your top choice. Okay? Another thing, this technology could become totally obsolete by the discovery of another much more efficient and quick to create energy. A source that takes minimal time to create, harness, and deliver. Or perhaps not. I mean, perhaps we will use an advanced form of nuclear energy in the future, just a farther innovation to maybe terraform a planet, or create a star, or any number of a billion other things we can do in the exponential growth we see in our scientific community today. So I think that's a good place to end it for today. Thank you so much for watching Science on the Side. I've been your host, Liam Hickey, and your correspondent, McKinley Adams. Thank you for watching, and Liam out.
Fly me to the moon, let me play among the stars, and let me see what spring is like on Jupiter and Mars.